Okay, so let me continue with that applications of uniform circular motion, advanced circular motion. So yesterday we have done advanced circular motion. Just a brief recap. We said that the angle swept by radius vector is called theta. Radius vector is line joining center of the circle to the particle, and angle swept by radius vector is called theta. Rate of change of theta with respect to time will be angular speed omega, and rate of change of omega will be alpha. If alpha is constant, we can write similar equations like omega is omega naught plus alpha t, just like our kinematics. Theta is omega naught t plus half alpha t square. Okay. Or omega is, sorry, theta is omega plus omega naught by 2 into t. This is also a very useful equation. Or theta is omega t minus half alpha t square, or omega square minus omega naught square is 2 alpha theta. These are our equations if alpha is constant. Then we also have alpha is, if you divide these two, omega d omega by d theta. This one. This is also useful sometimes. Okay. Then what I said is the relation between linear and angular quantities. Linear, angular. So we said L, the distance traveled by the particle in circle, is radius into the angular displacement. If you differentiate this dl by dt gives you speed is r into d theta by dt is omega. If you further differentiate this A tangential, because derivative of speed is not total acceleration, it is tangential, is r alpha. And of course there is a radial acceleration which is v square by r. But now that we have already seen that v is omega r, so we can write it as omega square r. This is also very important. So then we saw the applications of this angular kinematics and the circular motion. One was the conical pendulum. Just very briefly, I will revise this. Conical pendulum. So in this, what happens is you take a stone and rotate it as if it's going in a cone like this. Okay, this length is L, and basically you are giving an angular speed omega to this stone, and it goes in certain circle whose radius is, if the angle is theta, the radius is L sine theta. So we are supposed to find theta. So we can draw the free body diagram. There is tension and there is mg, and there is a radial acceleration omega square r, which is L sine theta. R is L sine theta, and this angle is theta. So we have t cos theta is mg in the vertical direction, because vertically this is in equilibrium, and t sine theta is mass into acceleration m omega square L sine theta. Sine theta gets cancelled. You can put this t back there, so you get m omega square L into cos theta is mg, and m gets cancelled. So from here I can find omega, or you can find theta, whatever, depending on what is asked. For example, theta is g by omega square L cos inverse. Cos inverse g by omega square L. Or you can say arc cos, that is much better way of writing. G by omega square L. But cos theta always lies between -1 and 1. So if this conical pendulum is to work, g by omega square L should be less than or equal to 1. Or omega must be greater than or equal to root g by L. This must hold. Otherwise, you can't keep this pendulum in this position. So this is one thing. So always in these questions, what we are doing is, in the radial direction, net force is m into radial acceleration, which is omega square r. Okay, so our main point is radial acceleration is omega square r. That is our main point. So you apply Newton's laws in radial direction and you use that. Mass into acceleration, you will use this acceleration. In other directions, if there is acceleration, you will use that, or it will be in equilibrium. Then we talked about death well, where you had a cylindrical drum like this. And you are standing on the base, and then what happens is the drum is given certain angular speed, and after reaching certain critical angular speed or more than that, the base will be removed. So this person will be kind of sticking to the wall and no base is there. So what is happening? He is going in a circle of radius r with angular speed omega. So in the radial direction, the normal force acting on the person is mass into radial acceleration, which is m into omega square r. So I got the n. So as you increase the omega, the n will be more and more because it has to support the radial acceleration. N is the adjustable force, it will adjust. So I can claim from here, as omega increases, n increases. What is the advantage of increasing n? Mu n, the limiting friction will then be more and it can balance your weight. So I can say in the critical case, at critical omega, n is such that mu n equal to mg, or mu into m omega square r is mg. Okay, so I get the critical omega from here. Omega will be g by mu r under root. So omega will be g by mu r under root. So our omega should be greater than this for safety in this death well. So omega must be greater than root g by mu r. Then what happens? Then the normal force is huge, limiting friction is huge, and only static friction will be enough to balance your weight, and you will be happily sticking to the cylinder. You won't fall down. That's the idea. Then today we will look at another application, which is basically banking of roads. Banking of roads. So what's happening is, when you have certain road, let me just try to adjust this. Okay, so when you have a road and suppose there is a vehicle going there in a circular path. So what is the force responsible for, because it's going in a circle of certain radius r, what is the force which is responsible for this circular motion? So the force is friction on the wheels. So when you turn a car, there will be a friction like this acting on the wheel in the side direction. So when you are turning the steering, okay, suppose you are turning the steering to the right here, the wheel would like to turn to the right, but the road will uh, exert a force on the wheel. So wheel is trying to turn to the right, it will push the road to the left in the process, and road will push the wheel to the right. Okay, road will push the wheel to the right, which that is the direction I am showing here, this way, with a force F. It is a static friction. Why? Because it is acting sideways on the wheel. Okay, the car is not skidding sideways. It is a static friction. So the static friction is responsible for mass into acceleration n v square by r, or m omega square r. I would want to write here v square by r, because here I am interested in the speed of the car, not omega of the car. Now what happens is, as you try to increase the speed, while taking a turn, you are demanding from friction more and more value. And this is a static friction. It is acting sideways on the wheel. So as you try to take turn and you want to increase the speed, you are saying to friction, come on, I want to take a greater turn. I want to take a turn at a greater speed. So I want to have a greater acceleration. So you provide me the greater force. Friction says, okay, I'll adjust. But it cannot adjust forever. It can go up to mu n. So there comes a point where mu n will be mv square by r and n will be mg there. So there comes a point where mu n is mv square by r. Okay, and n is mg because vertically there is n and there is mg. These forces are balanced. So mu mg is mv square by r. So v is root mu rg. V is root mu rg. When you are taking turn at this speed, the friction is reached its limiting value. If you now try to increase the speed and say to friction, come on, you also increase, it cannot increase. The bonds will break, the sideway bonds, and the car will skid. The car will skid. In which direction it will skid? Friction was supporting it and not allowing to go outward. Okay, it was applying a force inward. Now when bonds break, the car will skid outwards. That is, it will skid in this direction, outward, away from the center. So while going, instead of taking a turn on this path, it will skid and maybe go there. Okay, it won't be able to go in the perfect circle. It will go away. So for this reason, there is a limit on the road. You cannot go beyond that speed. But suppose it's a highway and people would like to go at high speeds, then what to do? So if it is a normal road, the car or the bus will skid on that road while taking a turn on the highway at high speed. So what they do is they tilt the road inwards. That means this is raised a bit and this is slightly lowered so that the road is not flat but rather tilted like this. So let me try to show that here. So I would want to, it's a bit of tilt. Okay. Okay. So there is a tilt actually. So now what happens? The car is actually tilted and it's trying to take a high speed turn. So compared to a flat road on which you are taking the circular turn, on this tilted road, you can go at a slightly higher speed and still take a safe turn. Why like that? So let us see that. So basically, previously it was a flat road and this is the back side of your car or bus or whatever. Back side. Okay. I'm showing such a diagram. Actually, the bus or the car was something like that. The road was going like that. I'm showing the back side. Okay. So for convenience, let's draw it like that. Now what you have done, you have tilted the road. So now the bus or the car is like this, the back side of it. It will be like this something. What are the forces on it? Let's try to draw them. There is now N. Suppose this road is tilted by an angle theta. There is N. There is mg. And of course now there is friction this way. Okay, static friction which is acting, assuming that this bus is not skidding. Static friction and it's going in a circle. Let me try to adjust this. So it's going in a circle like that on the tilted road. The road is tilted and it's going in a circle. So let us say this radius is r. It's trying to go in a circle of radius r. And now the speed is v. Now let us find the critical speed where limiting friction acts. The previous case on a flat road, when limiting friction was acting, the speed was root mu rg. We found it here, root mu rg. This is the critical speed on flat road, flat circular road. If you exceed the speed, the car will skid. If you go with lesser speed, you are safe. But now I want to calculate the critical speed here, which means again my friction has reached the value mu n here, critical value. So let me try to split the forces into horizontal and vertical. It's going in a horizontal circle. Even though the road is tilted, but it's a horizontal circle like that, right? That's what we are trying to look at. So let's draw the free body diagram now. Vertically, I have n cos theta in the vertical direction. There is mg. There is f sin theta. F is mu n sin theta because the friction has reached limiting value vertically. These forces must balance. So n cos theta is mg plus mu n sin theta. Horizontally, n sin theta, this component towards center, this n component towards center, n sin theta. If n is sin theta, friction will be cos theta because they are perpendicular. So mu n cos theta, both are towards center. It is m into v square by r. Now this is the critical speed because we have taken friction as mu n. If you exceed this speed here, again it will skid. But I am trying to calculate this speed in the case of a banked road. Banked means the road is making some angle with horizontal. It is tilted road. Okay. So let's get the speed here. So we'll eliminate n here. So first equation, if I keep all n terms on left side, n into cos theta minus mu sin theta is mg. That is first equation. And n into sin theta plus mu cos theta, second equation, will be m into v square by r. We will divide both these equations. So I have sin theta plus mu cos theta by cos theta minus mu sin theta is v square by rg. So I can write it as tan theta plus mu by 1 minus mu tan theta. What am I doing? I am dividing numerator with cos, denominator also with cos. I am dividing this with cos theta, this also with cos theta. Both I am dividing with cos theta. Then I am separating the terms. Sin theta by cos theta is tan theta. Mu cos theta by cos theta becomes mu. Similarly, here you get 1, here you get mu tan theta. So this will be v square by rg. So my v now in this new case with the tilted rod will be tan theta plus mu into rg by 1 minus mu tan theta. You see what was our previous value? It was, if you go here, mu rg. This term was the previous term, mu rg. Let me show it with a different color. This was the previous term, mu rg. But now to that you added another tan theta into rg and you have divided this with a fraction because mu into tan theta will generally be less than 1. So you are making it huge. This speed is much better than our previous speed, and even though you are going at higher speed now, you are not skidding. For example, let me take, suppose mu as, I'm just taking some values, 0.5. Okay, and I will take theta as 15 degrees. We cannot bank too much also. The road should be banked by less angle. If you bank too much, then a stationary vehicle will start sliding down. That is another danger. So let's check these values. So without banking, what is the maximum speed with which the vehicle can turn? I have here root mu rg. Without banking, V max is root mu rg. What is the radius that we are looking at? Let us say 5-meter turn you are taking. 5 meter is a very sharp turn actually. Maybe let's put 6 meters turn. Okay, 6-meter turn you are turning. Let's find the maximum speed here with which you can turn. Mu is 0.5, r is 6, g is 10. So you are getting it as 30 meters per second. I am obviously calculating it. So let me take my calculator. So 30 into square root 5.477 meters per second. Let's convert it into kilometer per hour into 18 divided by 5. 19.71. That's like 20 meters per second. You want to take a 6-meter sharp turn on this road. If you exceed 20, gone. 19.71, not even 20, 19.7, approximately 20. So if you are exceeding 20, you are gone, it will skid. Now what we will do, this was without banking. We'll bank the road at 15 degrees. Now let's find the Vmax. For road banked at 15 degrees. So what is Vmax? Root tan theta plus mu into Rg by 1 minus mu tan theta. This is the maximum speed. Tan 15 plus mu is 0.5. R we took 6 meters, G is 10, let us say. Previously also I took G as 10. 1 minus mu 0.5 into tan 15. So let me check what this value comes to. So first of all, trigonometry. Let me see tan 15 in degrees. So it's coming out to be 0.2679, approximately 0.27. So 0.5 plus 0.27, 0.77 into 60 by 1 minus 0.5 into 0.27. Okay, so let me calculate this value. 0.5 into 0.27 is coming out to 0.135. If I subtract 0.865, so 0.77 into 60 divided by 0.865 power half is 7.3 meters per second. If I convert into kilometer per hour into 18 divided by 5, 26.3, that is 26 kilometer per hour. You can take a 6-meter turn at this speed. If you exceed 6 meters is a short turn anyway. Sometimes there are 10-meter turns and so on, for which you can go at even higher speed, it won't skid. But here, even after the road is banked by 15 degrees, you cannot exceed 26 kilometer per hour. So without banking, you are going at 20. With banking, you are going at 26 kilometer per hour. Not much difference here, but if you take a bigger radius, maybe there may be some difference. If you take a bigger radius, instead of 6 meters, you take 10 meters, then it will be a greater speed, obviously. Okay. Now there is another danger. If you bank too much, if you make the road huge like this, the stationary vehicle might start sliding down. In that scenario, what is the limit of that theta? Suppose there is a stationary vehicle, there is mg sine theta, there is n, there is mg cos theta, there is mu n, which is mu mg cos theta in our case. So we should not have mg sine theta more than mu mg cos theta. So mg sine theta should be less than mu mg cos theta, or your tan theta should be less than mu. So you should bank your road in such a way that this condition holds. If this doesn't hold, stationary vehicle will come down. See, I am assuming that this force mg sin theta is less than the limiting friction. Okay, so tan theta should be less than mu. If you bank it like that, it's fine. For example, in our previous case, we banked it at 15 degrees. Tan 15, was it less than mu? We got tan 15 as some 0.26 or something, right? Just 1 minute. So we got it as 0.267, which is less than 0.5. That's okay. So you can even increase the angle here from 15 to slightly more value. As long as tan theta is less than mu, that's fine. So this is regarding banking. But sometimes, suppose if they bank a road too much where stationary vehicles start sliding down, then in that case, what you have to do, you should go with certain minimum speed, otherwise you will slide down. What is that minimum speed? You are going in a circular path with certain minimum speed. Generally, they don't design roads like that, but there is a problem given in HC Verma along similar lines. Somebody has designed a poor road where they have tilted the road by huge amount, where stationary vehicles will slide down. So in order to prevent this sliding down, the vehicle must go at a minimum speed, okay, where it's going with a minimum speed in a circular path. Let us say, so there is an acceleration v square by r, where the friction on the vehicle is at its limiting value now. Okay, if it doesn't go with certain speed, then it will slide down. Then the friction is kinetic now, it's no more static. So anyway, let's check this case. So there is n, there is mg, and it's going with certain minimum speed v min, so that acceleration is v min square by r. So again, the vertical direction, n cos theta plus mu n sin theta is mg. Forces are balanced. In the horizontal direction, n sin theta minus mu n cos theta here is m into v min square by r. Okay, so we can divide these two. So we have v min square by rg is sin theta minus mu cos theta by cos theta plus mu sin theta, which is tan theta minus mu by 1 plus mu tan theta. This is rg. So from here you get v min as root of rg into tan theta minus mu by 1 plus mu tan theta. This is the minimum speed with which the vehicle should be moving in order to prevent it sliding down. Otherwise it will slide down. Bad design of the road. So let's put all of this to practice by looking at a question. Yeah, let's look at this interesting question. So question is like this. Let's read it once. A turn of radius 20 meters. So there is a circle of radius 20 meters, which is a good radius, and it's maybe a highway road where there is a 20-meter radius, is banked for vehicles going at 36 kilometer per hour. 36 kilometer per hour. Let me convert into meter per second. 36 into 5 by 18. 10 meters per second. Let's understand this term. A turn of radius 20 is banked. Banking of roads we call it. Means tilting of road. This concept is called banking of road. Banking of road means the road is constructed not flat but tilted, inclined. Now this road is banked for vehicles going at 36 km per hour. What does that mean? That means that if the vehicle is going at 36 km per hour on this road, then no friction acts at that speed. If you now start increasing the speed, friction will slowly increase in value, and there is a certain maximum speed at which friction will reach static value. You shouldn't exceed that speed. Similarly, if you reduce the speed, again friction start acting so that you don't go down. There is some minimum speed where the vehicle is ready to go down. If you go lesser than that speed, the vehicle will go down. It will slide sideways. That's not good. So at 10 meters per second or at 36 kilometer per hour, no friction acts. That's how road is designed. Okay. So what is the and coefficient of friction he give? 0.4. Now what is he asking? What are the possible speeds for a vehicle so that it neither slips up, so maximum speed he's asking, and nor it neither slips down, sorry, slips down is minimum speed, nor skids up maximum speed. So he's asking both the maximum and minimum speed with which the vehicle can go. It shouldn't go greater than maximum speed. It should not go lesser than minimum speed in both cases. So let's see how this works. So first is we will try to get the banking angle. Suppose road is banked at theta and the vehicle, I'm showing the back side of the vehicle. The vehicle is going in a circle. Oops. Okay, let me try to adjust this. So vehicle is going in a circle. If it goes with 36 kilometer per hour, which is 10 meters per second, then friction is not acting. Then who is providing the centripetal force, in this case the force towards center? N's component. This angle is theta. Okay, how is that angle theta? You see these two lines? You see first these yellow lines. The angle between them is theta. Perpendicular to this flat fellow is N. Perpendicular to horizontal fellow is vertical. So angle between them is also theta. So I have N cos theta is mg and N sin theta is m into v square by r. Okay, radius is 20 meters now. Yeah, v is 10. From here tan theta is 100 by 20 into g. I'll take 10, so it is 1 by 2. So I got the angle at which road is banked. So the first statement, road is banked for a speed of 36 kilometer per hour or 10 meter per second, means at that speed friction is not acting. Normal is providing the centripetal force. So I got the angle of the road, banking angle. Now what we should do? Now he starts increasing speed. He shouldn't go beyond certain value. Similarly, he starts decreasing speed. He shouldn't go lesser than certain value. So first let's find the minimum speed. Suppose if he starts reducing the speed, somewhere the car wants to go down. Okay. So friction is up, mu n, there is n, there is mg, and it's going with a minimum speed. So v min square by r. So let's apply Newton's laws. In the vertical direction, n cos theta plus mu n sin theta is mg. In the horizontal direction, n sin theta minus mu n cos theta is mass into radial acceleration v min square by r. So let's divide to eliminate n. Sin theta minus mu cos theta by cos theta plus mu sin theta is v square v min square by rg. So v min, the minimum speed where limiting friction is acting, the car is just ready to go down, that is tan theta minus mu by 1 plus mu tan theta into rg. So let's see, sorry, I should take small eraser. So let's see what this will give me. Okay, so theta, we already got it. Tan theta is how much? 1 by 2, 0.5. So I'm going to put that minus mu. He gave in the question, what is mu? 0.4. The road and the tire coefficient of friction. 0.4 into r is 20 meters, g is 10, so it will be 200 by 1 plus mu. 0.4 into tan theta. 0.5. This we have to calculate. This is the minimum speed. So this will be root of 0.5 minus 0.4 is 0.1 into 200 is 20 by 1.2. So if I take my calculator, 20 divided by 1.2 square root 4.08, approximately 4 meters per second. So in kilometer per hour, 4 into 18 by 5 kilometer per hour. So 36 into 4 by 10, 6 4s are 24, 14.4 kilometer per hour. It shouldn't go lesser than this. If he goes slower than this, boom, he will slide down. 14.4. Let's get the maximum speed. How to get the maximum speed now? When he is going with the maximum speed, there is a tendency that if you exceed the speed, he will skid upwards. Because friction is acting down, it will break bonds and skid up. Okay, that is at a maximum speed. So again, n. So friction will be acting this way, mu n, and there is mg. So vertically, n cos theta is mg plus mu n sin theta, or if I rearrange, n cos theta minus mu n sin theta is mg. Horizontally, n sin theta plus mu n cos theta is mass into acceleration m into v square by r. So we'll divide these two. So sin theta plus mu cos theta by cos theta minus mu sin theta is v square by rg. This is the maximum speed I am calculating, V max. So what is the maximum speed from here? V max is root rg into tan theta, which we got 0.5, plus mu is 0.4 by 1 minus mu tan theta. Mu is 0.5 into tan theta is, mu is 0.4, tan theta is 0.5. So r is 20, g is 10. So 200 into 0.9 by 0.8, right? 200 into 9 by 8. Let's do the calculator. 200 into 9 divided by 8 square root 15 meters per second, or kilometer per hour. 15 into 18 by 5, 54 kilometer per hour he can. Safe bet on this. So minimum speed is, we got it as 14.4, maximum is 54. If he exceeds maximum speed, he will slip upwards. If he goes lower than minimum speed, he will skid down. I mean, he'll go down along the incline. So the road is kind of, tilted. Okay, maybe I want to show some visual. Okay, something like this. This is the vehicle which is going on the road. I don't know whether you can see, or maybe I should put like this. Yeah, so it shouldn't slide down while going, and it should not skid up both ways. Anyway, so that is the H.C. Verma problem. So circular motion, these are the main ideas which we have in circular motion. Let me show you a couple of more questions. Let's see one question, very interesting one. Suppose I have an inclined plane of inclination theta, and let us say this height is h. This is a smooth incline, and there is a block of mass m kept here. Okay, this wedge is rotated about this axis with omega. Find omega so that m is at rest on the wedge. So in the wedge frame, m is not sliding down. In the ground frame, both wedge and m are rotating in circle. How is this possible? Now let's try to see this. I will introduce a new concept here, but first let me solve it in ground frame. Solution in ground frame. Okay. See, the block is not sliding down on the wedge. So it is as if it is attached with some Fevicol kind of structure. It is like that. It's not attached with Fevicol, but it's not sliding down means it has no tendency to come down. How is that possible? See, if I draw free body diagram, there is N and there is mg. Okay. If I give sufficient omega, who will support that omega? Horizontal component of N. Horizontal component of N will support that omega. So as I increase omega, this horizontal component of N will increase, and at some point the N will take such a value where its vertical component is also balancing mg. See, if N is small, then vertical component may not balance mg. So I am increasing N. How you are increasing N? By increasing omega. So if I apply Newton's laws in horizontal direction, N sine theta is mass into acceleration omega square r. This is the radius. That radius you can get by doing trigonometry. Tan theta is h by r, so r is h cot theta. So I write like this. And N cos theta is mg. So from here I can get omega. So if I divide, tan theta is omega square h cot theta by g, or I can write, I'll bring that cot also this side, it will become tan. So omega square is g tan square theta by h, or omega is root g by h tan theta. If you rotate with this angular speed, the block will stay at rest in the wedge frame. In the ground frame, both are rotating. This is one method. So what did I do? If it is to remain at rest with respect to wedge, it means it is going along with the wedge in a circular path. The radius is r. You can get r by using trigonometry. Tan theta is h by r. So h is so r is h cot theta. Then I am applying Newton's laws in radial direction, and vertically there is no acceleration, so forces balance out. So vertically n cos theta is mg. Horizontally n sin theta is responsible for the radial acceleration. So as you keep increasing omega, n increases, and at some point that n can take such a value where n cos theta will be mg. So for all this to happen, the omega should be this. Now I did this problem in ground frame. I can do this problem in wedge frame, which is an accelerating frame. Solution in wedge frame. How do I do that? See, suppose I also go along with the block in a circle. I am the observer. I am also going along with the block in a circle. So not only the block is accelerating, I am also accelerating. Okay, what is the angular speed of mine? Omega only. So what is the acceleration? Omega square r. So observer goes along with block in circle of radius, whatever we previously calculated. What is the radius? H cot theta. So what is the acceleration of observer? Omega square r, omega square h cot theta. So observer is non-inertial observer. He is going along with the wedge, along with the block. So he is also going along with the block in a circle. So his acceleration is towards center. So if he wants to apply Newton's law, he has to apply pseudo force on this block. Pseudo force will be mass of the block into his acceleration. Then there is N and there is mg, and all these forces are keeping the block in equilibrium in his frame because he is going along with the block. So for him, block at rest. For him, block at rest. So these forces should balance. You can directly balance forces along the incline because N has no component along the incline. So you can directly say mg sine theta is m omega square h cot theta cos theta. So m goes away. So from here omega square is g tan square theta by h. So omega is root g by h tan theta. It's exact the same value we are getting. whatever you got here, root g by h tan theta, you got in non-inertial frame also. Now look, I will introduce a new concept. This force which you drew, this is a pseudo force. How did you draw it? Observer is accelerating towards center of the circle. So pseudo force is in opposite direction. This pseudo force value is mass of the block whose free body diagram you are drawing into observer's acceleration. This is called centrifugal force. Why centrifugal? Centrifugal means away from center. Centripetal means it is towards center, but you see the direction of this force is away from center, so it's called centrifugal. So centrifugal force is a pseudo force. It doesn't come in ground frame. You go and check the free body diagram. Nowhere there is centrifugal in ground frame. Centrifugal came in a rotating frame. When the observer was rotating, it came into picture. It is directed away from center, centrifugal. Okay. So centrifugal force comes into picture when observer is rotating along with some object whose free body diagram he is trying to draw. For him, the block will be at rest because he is rotating along with the block. But because he is non-inertial, he must apply pseudo force which is away from center. That's called centrifugal. So centrifugal force cannot come in ground frame. It will come in a rotating frame. Sometimes, chemistry teachers say in atomic structure, centripetal and centrifugal balance. They say electron is, suppose there is nucleus, electron is going in a circular path, right? This is centripetal and centrifugal are balancing. Why are they saying that? Centripetal is the force of attraction on electron due to positive charge in the nucleus. Okay, how come centrifugal came into picture? So they are actually going along with the electron in a circular path, and hence they are non-inertial observer. They applied a centrifugal force. So centripetal and centrifugal both balanced, so for them electron is at rest. In the ground frame, how do we write it? See, let me give a bit of basics here. Suppose the nucleus has charge q1, the electron has charge q2. So the electron is attracted with a force k q1 q2 by r square. That is what is centripetal. So if you observe in the ground frame, this attractive force on electron by nucleus is mass into acceleration of electron, which is v square by r. Acceleration in circular path is v square by r. Electron is assumed to be going in a circular path around nucleus. This is ground frame analysis. But suppose you also go along with the electron, then what do you see? Of course, you will see the attractive force on electron by the nucleus. That's a real force. But because you are also accelerating with v square by r, you will apply pseudo force, mass of the electron times your acceleration, and you are going along with the electron. You see electron at rest. So this is the centrifugal force, centrifugal, and you write k q1 q2 by r square is mv square by r. The equation is same, but your interpretation is different. In rotating frame, electron is not moving at rest, net force is 0. There is a pseudo force also mv square by r. Okay, but in the ground frame, how you are writing? Mass into acceleration, where acceleration is v square by r. Centripetal acceleration. Okay, so who is responsible for centripetal acceleration? This k q1 q2 by r square. That's why it's called centripetal force, the attractive force by nucleus on electron. Coulomb force, we will say. We'll see it in second year. So Coulomb force is centripetal. In ground frame, that is equated to mass into acceleration. In rotating frame, that is equated to centrifugal because the electron is at rest. Ultimately, the equation you get is same, but your interpretation is completely different. In the ground frame, there is only one force causing acceleration. In rotating frame, there are two forces keeping electron at rest. Because in rotating frame, if you go along with electron, you will see electron at rest. So that's the distinction. So my point is centripetal force, which is in the case of electron, the Coulomb attraction. In the case of a stone going in a circle, the tension due to string. In the case of moon going around earth, it will be gravitation. So this will be there always, there in all frames. The centripetal force is there in all frames because it's a real force, right? Whereas centrifugal force. This is a pseudo force. Comes into picture when observer is in rotating frame. He is going along with that object which is also rotating. Comes into picture when observer is in rotating frame. Why is it called centrifugal? Centrifugal means away from center. Because if observer is going in circle, he is accelerating towards center. Pseudo force will be opposite to his acceleration. It's away from center. So this pseudo force is called centrifugal force. It comes into picture only when observer is in a rotating frame. If he is in ground frame, there is no centrifugal. Centripetal is there in every frame. Centripetal is real force. Real force will be there in all frames. Pseudo force will be there only if observer is in non-inertial frame. That is the idea. In ground frame, observer sees an acceleration. But in rotating frame, he sees the electron to be at rest. No acceleration. But ultimately, whichever way you do it, the final equation is going to remain same. This is the verdict. Okay. So this is the verdict. Now let's go ahead. So we solved that question. Let me take one more question. Suppose I have got a spring, okay, whose natural length is L naught. Say L naught is natural length of spring, and the spring is attached here, and you connected a block of mass M, and this is rotating on a table in a circular path. Okay, so I don't know how to show it. Maybe I'll show it like this. Okay, this is a better diagram. So the block is being rotated with an angular speed omega. Block is going in circle. Angular speed is given. Natural length of spring is given. Find expansion in spring. This is the question. And this is a smooth table, no friction. So obviously the spring should be expanded, right? If spring is in natural length, it won't exert force on the block. If it doesn't exert force towards center, why will block go in a circle? Okay, whenever something has to go in a circle, there must be force towards center. See, even for example, Earth, Moon was given velocity like this. There is a force towards center, so Moon fell down. If this force was not there, Moon would go straight like that. After Moon falls down, it wants to go like this, but again Earth attracted, so it again turned. Again Earth attracted, it again turned. If Earth stops attracting, then Moon would go in the tangential path. So whenever something is continuously turning and going in a circle, there must be force towards center. So here, if it is going in a circle, obviously it cannot go in a circle of radius L naught, because then who will provide centripetal force? So it will go in a circle with some expanded spring. So maybe the spring is expanded so that its new length is L naught plus x, and block is going in a circle. So what is the spring force here? Kx. Spring constant I have not given. Let us say spring constant is k. So kx is the spring force. Okay, so this force is responsible for acceleration of the block, m into omega square, because it is being rotated with omega. Radius is L naught plus x. So k is given, m is given, omega is given, L naught is given. You are asked to find x. So we can get it from here. So kx minus m omega square x is m omega square L naught. So from here, x will be m omega square L naught by k minus m omega square. This will be the expansion in the spring. Here, if you see the result, the denominator, you got k minus m omega square. Suppose I ask the question, what if omega is, I want to rotate it with such an angular speed, which is k by m under root. That is, denominator becomes 0. If you want to rotate with this omega, it is not possible. The spring has to expand by infinite amount. Why it has to expand by infinite amount if you want to rotate with this angular speed? You can see from the mathematics that, if k is if omega is root k by m, If you put it here, x will be infinity. The expansion in spring will be infinity. But why like that? Physically, what is happening here? So let's and try to understand. I don't know how to explain this physically. It has some relation to a topic which we will do later, which is simple harmonic motion. Okay, it is some kind of resonance condition actually. We will see it in a later chapter also. But let me try to give some sense here. Let me think. See, it's something like this. I don't know how to explain. I'll try my best. You want to take it in a circular path. Okay, it cannot go in a circle. So spring must exert a force. So for which the spring will expand and say, hey block, don't go in this circle, go in a different circle so that I can expand and apply force on you. Now after the spring expands, the problem is the acceleration became even more. Initially it was trying to go in a circle of radius, suppose L naught. The acceleration demanding was omega square L naught. But even for this acceleration, spring should expand, let us say. So spring expanded by x and said, okay, I'll exert a force to provide this acceleration. But the moment spring expanded is not going in a circle of radius L naught anymore. It's going in a circle of radius L naught plus x. Acceleration has increased. Spring expanded to create this acceleration. But the moment spring expanded, the block is going in a bigger circle and it says, no, 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 now my acceleration is not old one. It is new one. So spring, your force is not sufficient. Okay, spring says, okay, I will try to increase my force. But how will spring increase its force? It will send the block even further. It says, yes, I have increased my force now. I will exert this force and create the acceleration that you want. But block says, boss, because I went farther, I am going in a bigger circle with same omega. My acceleration is even more. So now you increase your. So this continues. There is no end to this. I hope you understood the logic. So initially the block was trying to go in certain circle. Let us say of radius L naught, natural length of the spring. How will it go in a circle? There must be some centripetal force. But spring is in natural length. So how spring can support the block? It cannot. So spring says, I will expand a block, go a bit further, expand me so that I can exert a force on you and create omega square L naught. So block went farther, spring force became kx. It's trying to exert this force and create omega square L naught. But block says, hey, wait, now I am not at L naught from center. I am at L naught plus x from center. So I demand more acceleration. Your force is not enough to provide that acceleration to me. Increase more. So spring says, okay, if I have to increase my force, you have to go farther. So block will go further. Spring force increased. Now it is trying to cater to this acceleration. But block went farther now. Its acceleration is even more now. So there is no end to this. So that is what happens if k is m omega square or omega is root k by m. So if you are trying to rotate with that omega, you are screwed. The expansion will be infinite. So this is the what should I say? The explanation. But there is a very interesting explanation if we go into SHM or some forced oscillation kind of structure or natural and forced oscillation and resonance. Some kind of such concept exists in certain other topic which I'll explain there. So that is as far as circular motion is concerned, advanced circular motion. Now we have done vertical circular motion where we used work energy and Newton's laws in radial direction. We have done angular variables and circular motion and these kind of problems. We are now all set to enter the new chapter, which is center of mass and collisions. Very interesting chapter. So I have more or less completed work energy and circular motion together. So we'll close it here, this part. Any doubts that you have, you ask me if you have any doubt. Otherwise, we'll stop.
No, sir.
Cool.